We resume our story today with probably the most important concept that we're going to be able to use this semester to tell different groups apart from one another. After all, that is the large part of what we want to do this semester. Is now that we know what groups are, our big question, capital B, capital Q, big question for the semester is what groups can exist? Right? What are the possibilities? In one of our earlier activities, you had an opportunity to play with 4 different groups. You didn't know they were groups at the time, but it does turn out that they're groups. You were making multiplication tables for them. That now that we know that they're groups, we can call them Cayley tables for those groups. And at the end of the day, you decided that 3 out of those 4 were, in fact, reflections of the same kind of structure, and that there was an odd one out. The 4th one was different from the other 3, right? And so the question of how many different ways are there to make a group with 4 elements in it, the answer to that question is therefore at least 2. Right? There's at least 2 different, fundamentally different structures we can make if you give me 4 elements to work with. Right? So that's the kind of question that we would love to have a more general answer to. If you give me a finite set of elements, let's say n elements, how many different structures, how many different group structures can we make? And the word different here is probably the slipperiest part of this statement. Ultimately, at the end of the day, we can define a structure just by a Cayley table, a multiplication table for it, right? But to define what different means is actually one of the big projects that we have to figure out over the next probably 3 or 4 weeks it's going to take us to really come up with a good understanding of what different means, because at the end of those 3 or 4 weeks, we're going to come up with a good definition of what same means. Right? If I have 2 groups that are the same with giant scare quotes around the words, then we'll understand sort of from a definitional perspective what that means in a while. But for now, the best tools that we have is to detect when 2 groups are different. And so one of the best diagnostic tools to determine when 2 groups are in fact different is the notion of order. So if you had an opportunity to look at the daily work videos, this question is directed to you. There are 2 different ways in which we use the word order. What are they? One of the ways is to speak of the order of a group, and that is, as you say, defined to be the number of elements. So, for example, all of the groups that we studied in the last, in the multiplication table exercise, what was the order of those groups? So you have them listed on the page in front of you again. What would you say is all 4 of those groups have the same order? What is their order? 4. It's the number of elements that you're given to work with, right? So that's one sense in which we use the word order. And so let me ask you this question. How might we be able to use that idea to tell when 2 groups are different? What would we expect 2 groups... what would be, how do I want to say this? How can the order of a group tell us whether 2 groups are different? Do you think? Yeah, Kenzie? Yes, exactly. Groups with different order have got to be different groups. Their multiplication tables, their Cayley tables would have to have different dimension, right? And so they couldn't be reflections of the same Cayley table. So groups with a different order, number of elements, must be different groups. So right away, that gives us one diagnostic criterion, right? If my group and your group have a different number of elements, we cannot be talking about the same group. There's no possible way. So that's order of a group. What's the other sense in which we use the word order? The order of an element in the group. And how is that different? How do we define what the order of an element, let's say G, inside of a group G, is? The order of the element G is an answer to the question, how many times do I have to multiply G by itself before that product becomes the identity element in my group. So this is defined to be the minimum such number. So it's the minimum positive integer k such that g to the k power is equal to the identity element in my group. Now that's a super valuable definition, because what that definition is going to let us do is it's going to let us try and get at a converse to this statement over here. Groups whose orders are different have to be different groups. But what about groups whose orders are the same? Do groups with the same order have to be the same group? What do we already know about that? Not necessarily. How do we know, for example? So we've already seen examples of two groups that have the same order, the same number of elements, 4 elements, but in fact are different groups because their multiplication tables were different. How do we detect that difference is the question. Can we use the orders of elements to detect differences between groups? That's the question that I want us to start thinking about today, with the expectation that if two groups are the same, if they're not different, if two groups are the same, that means that their elements have to have the same orders. Their elements must have all the same orders. Right? For every element of order 17 in one of my groups, there must be an element of order 17 that corresponds in the other group, right? And so on, and so on, and so on. So if I have a group that has a ton of elements, I should probably check the orders of all of them. And if I come up with a disagreement, a group that has an element of order 8, but the other group doesn't have an element of order 8, then I know for sure those groups cannot be the same group. Because if two groups are the same, they should have elements of the same order in both.